Hi, it's Robin. Happy leap year if you're watching this in 2024, or I suppose 2028 or 2032 or whatever. And if you happen to be watching this on February 29th, then happy leap day. I thought it'd be fun to write some Commodore 64 BASIC and assembly language code to calculate leap years, but first I'd like to discuss what leap years are and why they exist. You might think everyone knows this, but I asked a bunch of people to explain the what and the why of leap years and was surprised how few people could explain it. So just skip ahead in the chapter index if you don't want to hear this. So while some of our units of time are perhaps kind of arbitrary, things like days and years are based on real properties of our Earth and solar system. A day is the time it takes for the Earth to rotate one full revolution around with respect to the sun. Or if you're geocentrist, a day is the time it takes for the sun to rotate around the Earth. And a year is the time it takes for the Earth to go all the way around the sun, a complete orbit. Now that's about 365 days, and if you add up all the days in our regular calendar with 28 days in February and 30 or 31 in the rest, so if we add them all up, that totals 365 days. But it actually takes about a quarter of a day longer for the Earth to orbit the sun every year. So gradually our normal 365-day calendar gets out of sync with the solar year. Every 4 years, you're off by about a day. After 100 years, you'd be almost a month out of sync, and eventually you'd have winter weather when the calendar said it was summer, or the other way around. So the solution is to add an extra day to the calendar periodically to make our calendar match up with the solar year. People actually realized this was a problem at least a couple thousand years ago, and in fact, Julius Caesar made this extra day solution official with the Julian Calendar way back in 45 BC, which added an extra day every 4th year. So most years are what we call common years, and they are 365 days long, but leap years are not common. They've got an extra day, 366 days total. That day is added to the shortest month, February. Normally 28 days. It gets bumped up to 29 days for a total of 366 days. Okay, so we can write a little program that calculates leap years for places still using the Julian calendar, like parts of Morocco, apparently. So if we go for year equals 1850 to, say, 2150, that's about 300 years. And then the math is if y minus the integer of y divided by 4 times 4 equals 0, then we'll print out y. And then next. This is actually just taking the modulus of y, but because C64 BASIC doesn't have a modulus operator, we have to do it this kind of ugly way where we have to take y, divide it by 4, take the integer of that to drop any fraction, multiply it by 4, subtract all that from the current year, and if that equals 0, that is, if the year evenly divides by 4, then we'll print out y, because it's a leap year. So we'll run that. And there we go. It's printing out all the leap years between 1850 and 2150 from 1852, 1984, that was a good one, the year 2000, and all the way up to 2148. Okay, so that's the Julian calendar, but you probably know that most of us don't use the Julian calendar anymore. Way back in October 1582, the new Gregorian calendar went into effect, at least in some places. It was an improvement on the Julian calendar, but it took some countries a while to upgrade. Greece apparently didn't start using it until 1923. But what's a few hundred years? So the main improvement is tweaking the leap year rules. I mentioned that the solar year is about a quarter of a day, about 6 hours more than 365 days, and that's why this leap year is added every 4 years, but actually it's a bit less than 6 hours. It's something like 5 hours, 48 minutes, 46.08 seconds. So those 11 minutes and 14 seconds a year do eventually add up. And from the time the Julian calendar was implemented to the 1580s, the calendar was something like 10 days off and was throwing off the dates of things like the spring equinox, the calculation of Easter. So they actually skipped a bunch of days in 1582, going right from Thursday the 4th of October to Friday the 15th of October. Yep, in 1582 there was no October 5th through 14th. So if your birthday happened to be October 12th and you were born in 1582, you wouldn't exist. You can't argue with science. Okay, so I was saying the Gregorian calendar added a couple more rules for leap years. Like usual, if it's evenly divisible by 4, it's a leap year, except if it's evenly divisible by 100, it's not a leap year. Except if it's evenly divisible by 400, then it is a leap year. Now, this might seem especially esoteric to us because the most recent year divisible by 100 with no remainder was the year 2000, and that was a leap year because it was divisible by 400. So it's like in our lifetimes, this rule does not seem to actually matter at all. It might as well just be divisible by 4. If I can derail us further, my great-grandfather was born way back in 1889, so he was 10 years old in 1900 when this rule did apply. February only had 28 days, despite 1900 being divisible by 4. And he was so long-lived that he didn't die until 1986. And actually, he was very interested in my Commodore 64 when he saw it. He said something like, "What's that there, laddie? A computer? It's like a television, but better. You can control what it shows." That's almost an exact quote of what he said. So the last non-leap year was 1900, and the next time we'll have a year divisible by 4 that won't be a leap year is 2100. I guess there's a decent chance my youngest kids will reach that year. So 200 years apart, 1900 to 2100, and maybe I'll have directly known people who will see those dates. Okay, so let's try and implement the Gregorian calendar leap year rules. Instead of regular Commodore BASIC, let's use Simon's BASIC, or Simon's BASIC. Which one to choose? Let's go with Simon's BASIC. Or is it Simmons BASIC? Ooh, crunch. So here we are in extended CBM version 2 BASIC. Kind of funny that after all that Simon's or Simmons stuff, it doesn't even say that when it boots. But let's use this because it has a built-in mod function that makes these calculations less messy. By the way, if you don't have a vintage Simon's BASIC cartridge, the cartridge image is easily found online. You can use a real C64 with something like an Easy Flash 3 or a Kung Fu Flash, or attach the cartridge image in Vice Emulator or on your C64. Okay, so to write the Gregorian leap year calculator, let's do the same thing for y equals 1850 to 2150. I just like that range of years and it fits on the screen easily. So instead of that trickier math, we can just use this mod function that's built in, taking the year, dividing it by 4, checking for a remainder of 0. So if that's true, it's a leap year. And if mod of y divided by 100 is not equal to 0, or if the modulus of y divided by 400 equals 0, then we'll print y, and the comma just makes it move to the next column so we can easily pack extra years on the screen. And then 30 next. Okay, let's give it a try. So here it goes. It's a little slower to calculate it. Okay, so you might notice that's a couple numbers less than before. The year 2000 is still there, divisible by 400. But importantly, it goes from 1896 to 1904. 1900 isn't listed there. And same here, 2096. The next leap year is 2104. Okay, so that's it in Simon's Basic. Thumbs up if you want more Simon's Basic in a future video. I really should do that sometime. Okay, so I've also implemented this in assembly language. So let's take a look at that. Again, I'll be using my Kung Fu Flash with the latest Super Snappy ROM from Adrian Gonzalez. At this time, version 5.34, and this is the NTSC version. Okay, and there's a D64 of my source code if you want to play along at home. So change directory command to leapyear.d64. And the latest source code version is 21. I just keep all my old revisions on there. Just do a dist directory with F3. If I find a bug or an update, I will add extra versions onto this disk image. So start Turbo Macro Pro, just load it ,8, 1, or just use the percentage sign. And start it with sys32768. Back arrow star also does a directory in the program. Source 21. Back arrow L to load it. src21, source version 21. And F2, that's Shift F1 to go up to the top of the source file if it's not there already. Okay, so this is more or less exactly a duplication of that Gregorian calendar leap year program that we just did in Simon's Basic. Of course, it takes a lot more code to do in assembly, but you might find this educational. You can see I did the same range of 1850 to 2150. Let's run the program. Back arrow 3 to assemble, and don't start it from here. It's best to back arrow 1 to quit out to basic, and I happen to have it at sys4096 to start. And there it is. And again, you can verify that the years, they're all divisible by 4 between 1850 and 2150, except that 1900 is skipped. And there's 2000, it's there. And here 2100 is not a leap year. Re-enter the assembler with sys32768. Okay, let's just walk through here. So I've got 2 0-page locations. These are low in memory, and these ones are free. Even when C64 BASIC and the kernel are in operation, these particular locations are available. FB and FC are going to form a 16-bit that holds the current year. And we also need a temporary variable that starts with the year, but we mangle it with a bunch of math while we calculate if the current year is actually a leap year. So temp is where we're going to do that work. Both of them are 16-bit values, so I suppose we could go all the way up to the year 65535 or something. But anyway, if you need to go past that, it's not going to work. Here's the start and the end years that I defined, and it should work with other ranges. I tested it a little bit with that, but I'm just using this just to standardize. Kind of back in the past a bit and into the future, centered around the year 2000. Which is the nearest year divisible by 400. Okay, now here's the program start. Star equals 1000 hex. That's just sort of arbitrary, but that's 4096 in decimal, so that's why we did a sys 4096. And here's the actual code beginning. We're going to initialize. We've also got a memory location called tab, and that's just going to be used so that we can also, in the assembly language, make those 4 columns matching the basic program. I had to kind of roll that myself, so we'll see that in a bit. Then we're going to set the 16-bit year to start, and we're just loading in that label, the low byte of it, and storing it in our 0-page location year, and then the high byte of it. 8-bit processor can only work with 8 bits at a time, therefore we have to split that 16-bit value into 2 memory locations, each with their own load and store. And here's our main loop of the program. We've started at year 1850. We're going to copy that year into temp. And as it says here, the process is destructive, so we're not going to operate directly on the year memory locations, but instead on these temporary ones. Just copying in the low byte of year into temporary and the high byte, that is the address of year plus 1, into the other temporary byte. And then we're going to jump to a subroutine called print if leap year. So that will both calculate if the current year we're checking is a leap year and print it if it is. And just in case you did run a really long program, here's a simple way. We're going to call this kernel routine FFE1. That just checks for the stop key to be pressed and just quits out of the program early. Just thought you might be interested in seeing how to do that, how to stop a program early in machine language. Okay, then we're going to go to the next year. I guess I could have said that, but it's just the same as the next line in BASIC. We're going to increment the current year, first incrementing the low byte, and if that's not equal to 0, we can branch ahead to check because it hasn't carried over into the next byte. But if it has wrapped around from FF hex to 0, or 255 decimal to 0, that's the maximum value that could be held in 1 byte. If it wraps to 0, then we have to increment the high byte of the year as well. Then we have to check, have we reached the end of the range of years that we're calculating? We're going to load the high byte of the year and compare it with the high byte of the end location. And branch if carry clear in this context means branch if less than. That is, if the high byte of the current year is less than the high byte of the ending, then we know we need to do another loop. So we'll just branch if carry clear back up to loop and do the next year. Otherwise, we're going to check the low byte of the year and compare that one. And if it's also less, then we will loop. But if they are not less, then that means we are done and we return from the subroutine, which just exits out to BASIC. That's the main loop of the program. All that's left is the actual tricky part of calculating, is something a leap year? That's what this subroutine is, print if leap year. And we're going to check, is the year evenly divisible by 4? We're going to divide our 16-bit year by 2. That's why we've copied it into this temporary variable so we can mess around with it. We didn't want to disturb the actual year that's counting up. We just want that to count up step by step. But to calculate if it's a leap year, we have to actually do some work with it. So we're going to shift it right. This is called a logical shift right. Because it's a 16-bit value, we start with the high byte, shift it right, and then the carry will fall out. And then we're going to rotate that into the low byte of temporary. Effectively, that's divided by 2. Now, the lowest bit of the year is going to fall off into the carry. And then we're going to check. Branch if carry set, that means if it's a 1, to not a leap year. So if the lowest bit of the year was 1, that means it's an odd number. Therefore, we know it's not a leap year right away. And we can branch ahead to not leap year, which just returns and goes to the next year. If it was a 0, then we're going to divide it by 2 again. So again, exactly the same thing. Shift the high byte and then rotate the low byte. The logical shift just puts a 0 in the high bit, while rotate takes the current carry and puts it into the low byte here. Now that bit is also a 0. Branch if carry clear, 0. Then we're going to go ahead to mod 100 or modulus 100 because both bits were 0. If not, it was an even year that wasn't evenly divisible by 4, and we're done. It's not a leap year. Okay, so if the program makes it to this mod 100 label, that means it is divisible by 4. All we have to do left is the really tricky part of calculating if it's divisible by 100 and 400, so we can decide if it really is a leap year or not. So what we're going to do is divide by 100, but since we've already divided by 4, what we're really doing is overall dividing by 400. We've already divided by 4, so we have to divide by 100 more. Okay, so this routine took me quite a while to figure it out. Okay, so there'll be a link in the video description to a page on Codebase 64. On that page is a 32-bit hexadecimal to decimal conversion by one of my favorite all-time coders. His name's Graham, and he made the Dawnfall demo that changed my world in 1996 when I first saw that. So even though it's a hex to decimal conversion, what I was really after was this. It's actually a divide by 10 routine, which once I figured it out a bit, I realized I could divide by 100 with it, and that's exactly what I needed. But it took me a while to understand it. So that's what I'll try and do now. The y-index is going to be used as a counter to make sure that we process all 16 bits that are in the year. And this is essentially implementing long division the way we learned to do it back in school, but that's in decimal. In this case, we're doing it in binary. So you have the number that needs to be divided, which is 16 bits long. We're going to make sure that the accumulator is empty and that the carry bit is clear. And then this is the main loop that does the division. First, it rotates the accumulator itself, which starts off at 0. So that doesn't do anything, but later it will accept an incoming bit. Then we compare the accumulator with 100, because that's what we want to divide it by. If the value in the accumulator is less than 100, then there's nothing to divide. Carry will be clear, so we just jump ahead to skip. But if the accumulator is currently 100 or greater, then we're going to subtract 100 from it. Just like when you're doing long division, the divisor, if it does fit in one time, you write a 1 at the top, and in binary, that's the only choice, 0 or 1. You write a 1 at the top, then you multiply it, and you subtract that 100 from the running total. Exactly the same thing here. So if the value was greater than 100, we subtract it. And the important thing here is that carry will be clear if the subtracting did not happen, if you couldn't fit the divisor into the value you're dividing. So now the answer is going to start getting slid into that same value we're dividing. It's really quite a clever optimization. Rather than keeping the answer off it and using more bytes for it and actually taking more cycles to process, all in one, it's going to start putting the answer on the right-hand side as the value we're dividing keeps going out the left edge of the 16-bit value into the accumulator. So now either a 0 or a 1 has entered, and that's the beginning of the answer. And then it rotates the low byte first, then it rotates that into the high byte of the answer. And now we're going to decrement y, which is the bit counter. And if there's still bits left, branch of positive. If there's still bits left, it'll just branch up to loop. And I'm pretty amazed that this tiny bit of code here, what's that, like 8 lines of code, can divide a binary number by a big value like 100. But it works. And at the end, the divided value will be in temp and temp1, the 16-bit value, and the remainder, which is the modulus, is going to be in the accumulator. So we're nearly done already. Basically, the remainder is like we did a mod 400, but again, because we'd already divided by 4, we're going to check for the 3 cases that happen every 400 years that aren't a leap year. So if the remainder is 25, 50, or 75, as if the remainder was 100, 200, or 300, but importantly not 0, or 400 you could think of it, then it is not a leap year. So basically every 400 years is a cycle, and 3 of those years are not leap years, even though they're divisible by 4. And these are those ones. So all those are not leap years. Otherwise, it is a leap year. And finally, we're going to print the value. We're going to load the low byte of the year into the X register, the high byte of the year into the accumulator, and make use of this basic function that will print a 16-bit number at BDCD. Note that this is only available if you have the BASIC ROM switched in and you're playing nice with BASIC, but it's a very handy thing. Now, unfortunately, there's no way, I actually looked into this. I thought there would be a way of advancing to the next tab. Just like in BASIC, you can use a comma to go to the next tab. I thought you could, print a tab, so to speak. I could not find a way. I checked with my friend Mr. Dornbos, and he didn't know of a way either, but it's not all that hard to implement ourselves, so that's what we've done next. So all I'm going to do is increment to the next tab. This is just a counter we have. Increment it, load it, and it with 3, which is like a modulus 4. The only possible results are 0, 1, 2, or 3. Once it goes to 4, and 3 forces it back to 0 again, and we store that in tab. And if it's not equal to 0, then we're just going to branch ahead. But if it is 0, that means we've reached the end of a line, and we need to print a carriage return, which is just character number 13, and jump to subroutine FFD2, which prints that new line and returns. And we're done. But if it's not a new line, then we need to still advance to the next tab in preparation for the next print. And that's just this bit of code here. We've got the tab number in the accumulator. We move that into the X register, and then we load from the tab table indexed by X and get the tab position into A. And that tab table is just down here, and it's just the column number 0, 10, 20, or 30, corresponding to the 4 tab positions available. So the accumulator will now contain 0, 10, 20, or 30. Actually, I suppose it never actually contains 0 because that's just handled by this new line, which automatically brings the cursor back to the left. Then we can get the current cursor position from the kernel. If you set carry and call FFF0, that will bring the cursor position, the cursor X and Y, into Y and X. Note that they're reversed from what you might expect. And that just has to do with how indexing works on the 6502. So they'll be the opposite of what you might expect. Now we've got the cursor position we want in the accumulator, so we have to put that in Y, which is the X position. Then we have to clear carry and call that same FFF0 plot, and that will set the cursor position to the Y and the X that we have specified. So it's just taking the current row, remains unchanged, but we've advanced the X to the next tab position, multiples of 10. And then we return, we're done. And that's just the temporary storage we're using for the result. Oh, actually, that's not even necessary anymore. Well, I'll leave it there, and the tab value that we were using. Result is something I did have right up here. It just ended up not being necessary. After you do the division, the modulus was stored. It could be stored in result if you needed it. But because I just did the compares immediately, the accumulator still had the correct value. Okay, so let's just assemble that again. Actually, here, I'll get rid of that result just to confirm that. Back arrow 3. Yeah, it assembles fine without it. I forgot to delete that byte. And back arrow 1 to go back to basic. And just to run that one more time. sys4096. Not super fast, but it works. Oh, and I just wanted to note, this is a funny coincidence I noticed while I was working on this in both basic and in assembly, because I'm dealing with binary and decimal. The significant years when doing leap year calculations in binary, if the year ends with the 2 bits 0, 0, that means it's divisible by 4. And the other rules are, if the year is 1900, in decimal, if it ends with 0, 0, then that's significant for the leap year. Do you see what I'm getting at here? A pair of zeros, whether you're in binary or in decimal, is what's used to detect if it's a leap year or not. That just seems like a really funny coincidence to me. Well, you know what? I just got to try this. Let's try and go from start year 0, year 0 to 65534. Yeah, let's try that. There it goes. Okay, so I hope you found that fun. Again, happy leap year, happy leap day. Thank you to my patrons for their support. Thank you for watching, and we'll talk to you next time.
Walking very slowly, being careful she doesn't slip. She must be new around here on this shiny ship. The stewardess struggles to walk with her Velcro bottom shoes. Bring dinner to me while we fly to the moon. messenger while the men pilot the craft.
What will it be like in the year 12,000?